Greetings Physics 109 students. So I'm making this video to help you with the first 5 problems in Unit 3. I'm going to go through them one at a time here. So we're going to start with number 1 where it says a runner of mass 63 kilograms accelerates from 0 to 6 meters per second in 4 seconds. Now again, most of you, or actually all of you, have different numbers than me. Not all of these numbers are going to match up, but in this problem in number 1 a mass is given. In this example 63 kilograms. In your example it might be something else. In this example, goes 0 to 6 meters per second in 4 seconds. So again, these numbers may vary, but how you work the problem is not going to vary. Now it says to find the net force using alternative form of Newton's second law. Just ignore the alternate form of Newton's second law. I'm not even sure what the author means there, but or whoever wrote it. But Newton's second law is force equals mass times acceleration. The mass you have, it's all about you need the acceleration, and you can get the acceleration from this. Your acceleration is change in v over change in t. In my example, the change in v would be 6 meters per second. Change in t, 4 seconds. So this is just a matter of putting the numbers in and getting a number out. So that's pretty much enough probably on number 1. Let's talk about number 2 here. Let's see, it says a microwave antenna with a mass of 84 kilograms. So I'm going to write this down, 84 kilograms. And again, your number might be different. Sits on a tower 40 meters tall. So that's some sort of height. And then it asks to calculate the potential energy relative to the ground. So potential energy is mgh. In this example, mass is given, a height is given, and the g is 9.8 meters per second squared. And that's pretty well enough on that one. All right, number 3. All right, so number 3, it says, as it orbits the Earth, an 11,000 kilogram Hubble telescope travels at 7,900 meters per second, and it's 560,000 meters above the surface of the Earth. So they're talking about, some sort of satellite. A mass is given. Mine says 11,000 kilograms. Yours probably says the same thing, I'm guessing. But a speed is given, 7,900 meters per second. And a height is given, 560,000 meters. So again, this problem is really just kind of calculations. Part A says what's the kinetic energy? So kinetic energy is 1/2 mv squared. And they give you a mass and a v. Just put them in, square it. You're going to get a really big number. So don't worry if you're getting something absolutely huge. When you take like 10 to the 3rd power and you square it, that's going to be like 10 to the 6th. And then 10 to the 7th, 8th, 9th, 10th. You're going to get a number around 10 to the 10th or 10 to the 11th power, and that's okay. All right, part B, what's its potential energy, assuming gravity is constant? I'd like to make a little comment here that gravity is not constant over that entire interval that far away, but taking their advice here, so the potential energy equal to mgh. So they give you a mass, put that value here. They give you a height, and g is again the 9.8 meters per second squared. One thing I'd like to comment about problems 2 and 3. These aren't really physics problems. These are just calculations here. There's no changes in potential energy, no changes in kinetic energy. These are what I would just kind of call warm-ups. Right? Problem 4 is the first one that actually is a problem in physics, where in number 4 it says a student drops a water balloon out of a dorm window 15 meters above the ground. What is the speed when it hits the ground? Well, so in problems like number 4, first thing I always want to do is draw a picture that kind of describes the problem. And I'm just going to do a quick sketch here. So we've got like maybe some sort of building, a window where a person opens the window and drops a water balloon. Oops. So here's my, window, and then here's maybe a picture of my water balloon. Now this is going to be what I'm going to call state 1. The water balloon is dropped, so it's going to accelerate down, and I can kind of show that graphically. Again, remember the motion diagrams, kind of like little snapshots in time. These distances getting bigger because the speed is increasing. State 2, the water balloon is just off the ground. Now you notice there's a little daylight there. We're talking about right before it hits the ground. It'd be moving this way with some sort of speed, and that's what we're looking for. So you notice I've drawn a picture, state 1, state 2. This height is given in the problem. Then you write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. This is the state 1. This is state 2. Now, Whenever you deal with potential energies, you have to define your datum. I'm going to draw that in blue. Usually the lowest place in your diagram is a good place to put your datum. The datum is the height at which we're going to measure our potential energy. Any object above the datum has a positive potential energy. Any object at the datum would have a negative zero potential energy, and anything below the datum would have a negative potential energy. And you can go below the datum. Imagine that somebody digs a well here, and so that this balloon can keep falling. So if it's down here, it would have a negative potential energy with respect to that datum. All right, so now going through this problem, PE1 is the potential energy, picture 1, which is going to be an MGH term. Now, this balloon was dropped. It doesn't say it was thrown. So at state 1 here, it's really not moving yet. So its kinetic energy there is 0. I'll talk about that work term last. PE2 is going to be 0 because the ball is now at the datum, or the balloon. And then KE2 is 1/2 mv squared. Now, the work term is 0. And let me talk a little bit about why. As this ball accelerates down, it's acting under just one force, the gravitational force. So if I were to draw a free body diagram for it, and a free body diagram is just a picture of the object showing all the relevant forces on it acting. There's only one force, mg. This force is doing work as we move from 1 to 2, and the work that it does is positive. If I were to calculate a value for it, it would be the force mg times the distance h. You'll notice we have that term right here, mgh. This is the work done by gravity as we move from 1 to 2. So if we put another mgh here, we will have taken it into account twice. So gravity's taken into account right here. There's no other forces present. That's why the work term is 0. And again, I believe that in this class, in this homework set, all the work terms will be 0. If I find one where it's not, I'll point that out in the video. All right. Number 5 is pretty well an identical problem. Well, let me back up. So put all your values in. I should have finished that off there, sorry. Notice that the mass can divide out of this, because if I divide everything by m, it's gone here. 0 over m is still 0, 0 over m still 0, still 0, and it's gone here. So put your value for g in, put your height in, equals v squared over 2. That's what 1/2 v squared would be. And then solve that for v. Right? Problem number 5 is identical. I mean, it's a different setup, but it's the same type of problem. A person jumps off a cliff 24 meters above the ground. How fast are they going when they hit the ground? Make sure you draw a picture. Draw the cliff, draw the person while they're jumping off the cliff, draw the person right before they hit the water, very similar to the balloon example. Write out the work energy theorem. If you measure your potential energy from the water, you will have a PE1 term equal to mgh, and you'll have no PE2 term. But you will have a KE2 term. So that's probably enough to get number 5 done. I'm going to stop this video right here and just make a separate video for the rest of these problems. Hope it helps. Have a great day.